Thank you for joining us on today's webinar Wednesday. Today's topic will be using SOLIDWORKS simulation for shock, vibration, and seismic testing. My name is Silvio Perez. I'm the simulation product specialist for Hawkridge Systems here, and I specialize in anything that has to do with all of our analysis tools. So definitely, if you have any questions, let me know at the end. But today is really about, the goal for today is really to inform you on the different ways we can approach a problem where you may have to follow some sort of vibration or seismic standard to apply to your model. You know, in my experience in discussing with designers, different engineers that may have to follow some sort of standard such as a mil spec, a mil standard, the question always comes up of what are the different study options that are available that can help simulate different scenarios where my model or structure may endure some shock or vibrational loading, or maybe even endure something more drastic like an earthquake. You know, ultimately, how can we approach these problems with our tools? And for those who may be familiar, who work in that industry, you know, or who are not familiar, you may be wondering, well, what does a typical standard tell me? What does a mil-spec standard tell me? Usually, really the purpose of them is to help you achieve standardized objectives that that standard has told you. So, for example, the U.S. Department of Defense will submit some sort of standard as far as a procedure that was done to test a certain structure or a certain model. It's kind of instructions on what standards to follow. And then it tells you what to consider when running a specific analysis type. And it may go into some information on what the test fixture was used to actually set up that problem to ultimately get information of, you know, how much stress or displacement there is that the structure is experiencing. All right, so what I want to do is kind of show you on a product-by-product basis how we can go from a simplified case, what are the assumptions that are based on that, to a more complex analysis to account for, again, shock or vibrational or seismic loading. So what you're looking at here is the product matrix for our SOLIDWORKS simulation packages. Simulation standard is the first tier. It gives you everything in the green tiles. That's related to this topic. You get a linear static analysis for parts and assemblies. Moving up the chain, you get simulation professional, which is the middle section. In the light blue, you get the light blue and the green capabilities as well, where we're pretty much giving you more study types depending on what you're after, such as a frequency, telling you things like the mode shapes or what the natural frequencies are of your part and structure, or a thermal study where you're seeing how hot your component's getting, what the temperature distribution is. And then we can graduate to a simulation premium seat, which gives you everything you see on your screen. So it gives you, you know, your basic linear elastic study to a more advanced nonlinear or dynamic analysis. So bringing that down to smaller chunks, you know, again, how do we approach a situation where we're dealing with shock or, you know, vibrational loads or transverse loading? You know, how do we account for that in a linear static way? So starting from SOLIDWORKS simulation standard, what we can do is we can run a linear static analysis, and really the best that we can do is define our material properties, how it's going to be restrained, and then our loading condition can be some sort of force, or in this case, it can be some sort of gravity load. So when we try to apply some sort of, or meet some sort of standard, or apply some sort of acceleration load that it might be experiencing, we can ultimately define it by applying some sort of gravity and possibly multiplying it by some sort of large number. So what I just popped up here was kind of an excerpt of something that we got from a mil-spec standard here, and it's giving me instructions on to account for any seismic forces that are acting upon my structure, to essentially apply gravity in the center of the model and multiply it by some large value that's defined by some table that they provided there. And they also kind of define the direction in which that acceleration is being applied. So when we go into the actual interface here, the example that I have is an electronics box, and I ran a linear static analysis, and what my goal is here is to kind of show you how far we can take it with that load type. So to kind of walk through the process of how I set this up, you see that my assembly consists of all these components here, right? We might, in this scenario, we might be concerned of how much stress the PCB board is experiencing, or are those capacitor stems going to endure some of the seismic loading that we're applying here, or anything about this model is going to tell us in terms of stress and displacement. So I apply the material models here. I can define contacts in terms of how the bodies are going to behave if they come into contact due to the load, or if they're already touching, I can assume that everything's bonded or glued together. And then I told the software that I restrained the model as if it was being bolted down in those 4 holes here. So we're imagining that this is attached to something here where it's going to experience some sort of seismic loading. So, and then as far as the external load that we apply, all I'm going to do is go into and apply into gravity. So you see that gravity, it automatically picked up that plane. It's saying that gravity is being applied normal or in the downward direction based on that top reference plane. So what we can account for here is kind of just the dead load, or the load due to just gravity. But in the case of where we're trying to fulfill that specific standard that was applied, where it's in the horizontal direction and it should be amplified by whatever was based on that table, we can turn on these advanced settings where we can add a multi-directional gravity load. In this case, let's assume that I want to apply 5 Gs in the horizontal direction of this model to simulate whatever was being done that was defined in the mil spec. So I can simply just hit 5 times 9.81. Right, that's going to be considered 5 Gs in that direction, and you see that we have that transverse direction on that model. All right, and we can add another direction as well, or we can, maybe we want to apply different scenarios. So I can accept this here, I can duplicate the study, all right, make a copy and define it as far as what I want to make a change for. I can edit this gravity here, maybe in this scenario, or maybe I don't want to apply a transverse loading in that direction. I want to apply it in the other direction, and maybe I want 20 Gs within that direction there. I can just update that value and duplicating that specifically, and you see that my arrow changes in that specific direction. So essentially what we can do in a linear static analysis is kind of take a conservative approach where essentially we're just magnifying the gravity load, right? We're trying to see kind of how bad the stresses are going to be and displacements are going to be by taking your gravity value and multiplying it by some very large number. All right, so if I go into my completed set here for the static analysis, the typical result that we get is a stress analysis here, and you see that essentially it's seeing some max stress where we can pinpoint exactly where that's going to be here, and you see that the max stresses are going to be in one of the stems of the capacitors here. So ultimately what you want to ask is this failing or not? Well, we compare the max stress to the overall yield strength of that material, the capacitor, and we ask ourselves if it's where we pretty much see if it's below the yield strength of the material property of that capacitor, then we're probably okay. If it's exceeding that value, then we probably have a problem. It's probably overstressing it, and it may ultimately be we may need to consider some sort of nonlinear problem to account for any plastic deformation that it might be experiencing. Reason being is that a linear static assumes that it won't have any large displacements, any large deformation, no permanent deformation. It's only going to assume that all the materials or all the components are going to behave linear elastically. So if I take a look at my material here, you see that the only material type I have is a linear elastic. So if we're kind of imagining a stress strain curve, it's only going to behave linear elastically. So anything that goes beyond yield, we may have to consider nonlinear. But nonetheless, this is a good, simple test that we can run to impose that seismic load that was defined in that mil spec sheet that I found. Right? And then we can take a look at our displacement. Right? We can see to what magnitude it's displacing. We can animate this as well. right, and obviously it seems really drastic right now. Keep in mind that we do have a deformation scale set to 1200 times. So in true scale, it's only really deforming 0.01 millimeters. So we take all this information and hopefully we have some sort of standard to follow that it shouldn't exceed a certain displacement or stress, and this is how far we can take it. Right? But what if I wanted to know, how the stresses were being developed as it was starting to load and then until the final load point? Unfortunately, we can't really do that with the linear static analysis. It assumes that the load is being applied slowly and gradually, and the results that we're seeing here are the stresses and displacements at the end of that load. Right? So it doesn't give us any information in between. So that's how we can approach it with the linear static analysis. So going back and taking it up further, what can we do in a simulation professional environment? So we still can do a linear static approach, but when we incorporate simulation professional, it actually provides us with this load case manager. So this load case manager is to define different load scenarios, meaning that we can define some sort of dead load or some sort of transverse loading or some amplified loading that we've defined in our baseline static analysis. And it prevents us from having to duplicate that original static analysis and comparing those results, and we can do it all within one interface. So the inputs of that we'll see here very shortly is defining the loading amplitude, any possible load combinations that I want to see, and we get our results such as stresses, displacement, strains, pretty much any result type that I can make based off a sensor that I define. So going back to simulation, you see that in a linear static environment, we have to run this baseline analysis to make sure everything's okay. But if I want to run multiple load scenarios, I can go into my study here, right-click, and I have the option to define a load case manager. And we get presented with this interface here. And you see that what it does, it takes the fixture and the loading conditions that I've applied in my baseline linear elastic study here, and we see that we can incorporate different load cases. So I have defined a few already where you see in my first load case, I want to see what the stresses are or what my results are based on 20 Gs, pretty much multiplying 20 times the gravity in that direction that's normal to the model. Right? And then I defined a transverse load that's 10 times the gravity that I've defined. So you see in that specific direction is 10 Gs in that normal direction. You see that I have the option to, well, in this scenario, I don't want a load to be applied in the normal direction, but I do want a load being applied in that transverse direction, and so on and so forth, right? And you see that I ended this with a dead load where I'm just seeing what the stresses are and displacements are due to that gravity load. And all I have to do is really just add an additional one here, and I can specify what scenario I want, either suppress it in that direction, define gravity in that direction, or I can override that and input whatever value that I want. Okay? So it's all based on whatever you define in your baseline study. I don't have any load combinations here. You see that I've done like a acceleration in the normal direction and in the transverse direction. We can actually create load combinations where I can take this information, these primary load cases, and say, well, I want to see the sum of these load scenarios and see what the results are based off that. Some sort of equation based where I'm utilizing these load cases and creating these different combinations. And then lastly, what I was mentioning is we can output any result that we want as long as it's based from our sensor. So you see that I'm interested in the stresses and displacements overall for the entire model. And then I also define what the stresses and displacements are at the actual PCB board. And the way I did that was just defining a sensor, these sensors that you've always had available to you in the normal modeling sense, where you say I want to pull information from my sim data, and I can output any result from this list essentially. And I may be interested in the strain or the overall factor of safety, and I can change my units, change what I actually want to output, the max, the minimum, the max over a selected entity, pretty much choosing an entity off the fixture or off the model. And once I run this load case scenario, I can go into my result view, and you see that we get those results that we're interested in seeing based off these different load scenarios. So it almost eliminates me having to duplicate that linear static analysis and having to edit the definition of each load case, where I can just combine everything into this one study and this one interface and literally choose the information that I want to learn from this analysis in this nice table format, where you see what my stresses are, displacements are due to those different load case scenarios. So a pretty nice tool that they provided. I believe they introduced it in 2015, but it's something that's available within Simulation Professional. Okay. So far what we've seen at the end of the day so far is the linear static approach. Again, this is more of guessing how much force will be applied to kind of represent that seismic force. You know, it's pretty much a conservative approach to see what those results are. But if we need more accuracy, if the standard requires, or if the actual test fixture that was done was through a shaker table, or if we wanted to incorporate some sort of seismic information, like what's the structure or my model going to do when it's experiencing some sort of earthquake, you know, those inputs are a little bit more complex that we can't really do within a linear static approach, but we can do that within the dynamic studies available to us in a simulation premium seat, right? So it filters down to these 4 products as far as the dynamic problems, and it's a way to check the response, or to see how the model responds to the loading conditions that essentially change with time. So if we want to account for a seismic loading, some sort of earthquake, we can run a response spectrum analysis where the input is going to be some acceleration, some velocity as a function of frequency, and the result that we get from that is a single response due to that shock load. So essentially, we get results similar to a linear static, where we're only seeing kind of the worst case scenario. You know, we're not seeing how the stresses are being developed throughout time, but we're seeing that worst case scenario. If we did want to see how the stresses and displacements are being developed from the beginning of the load to the end, or if we want to apply some sort of shock analysis or some sort of shock load, we can run a time history analysis where we can see those results as a function of time. And then a harmonic analysis is very similar to a time history, except the input now is as a function of frequency to replicate some sort of vibrational testing like a shaker table. Right. And if we take a look at a spec sheet again, you see that we can define it due to some sort of dynamic parameters that is defined. So in this spec sheet, it has some instructions on what the damping ratios are. So that's something that we can define within our linear dynamic problems as well. It has some parameters, some instructions to make sure that we've accounted for enough modes of vibration when it runs the frequency portion of a dynamic analysis. And we also have ways of changing the algorithm or the technique of how it generates the sum of these modal stresses that are being developed. So these are all parameters that we can change. So the more parameters that we're able to change or to input, the more accurate these results are going to be, essentially. So the first one that I want to show you from these dynamic results or from this dynamic analysis, is a response spectrum. Again, it allows you to perform a virtual test using what's called the shock response spectrum data. So it's a method of combining these peak responses of a structure from a range of frequencies. And essentially, it's a way to simulate seismic behavior, right? Some sort of earthquake, some sort of wind load, where it's a little bit random in its nature. But again, we want to see what the worst outcome is. What's the worst case scenario due to this response spectrum data? That's why it only gives us the peak response of the structure. Usually, again, some sort of mil standard or mil spec will provide that instruction or that data. We can also gather this information from the USGS, the U.S. Geological Survey website. It's kind of nice. You can pinpoint some sort of information or some sort of location, and then it'll give you this data, some acceleration as a function of frequency. And that's essentially what the input is. So taking a look at that, the way we do that here is when I go into my response spectrum study, you see that the input is pretty much the same as a linear static. We still have to apply our materials, what contacts are being defined, how it's being restrained. But now, instead of applying some sort of gravitational load or anything like that, we can define a base excitation. Essentially, how are we going to excite this model? And it's going to be due to that response spectrum data. So you see that we have the option, depending on what your data is a function of, it can be based off displacement, velocity, or acceleration. And the data that I found, it should be due to acceleration. You see that we have, I just input a multiplier of 1 Gs, and then I turned on this variation with frequency here, and this is what my response spectrum curve looks like. So from this frequency range here, it's going to see an acceleration of this amplitude. So essentially this column is a multiplier. So this first one here is going to see 0.025 Gs in the direction that I selected here. All right. So when I input that curve, you see that it's going in the downward direction. We can select multiple directions if we'd like as well. And when we do that, we can run the analysis. And again, what we're getting here is the peak response. So essentially the worst case scenario of this stress. So you see that, due to that given data that we define, this is the stresses that will be developed due to that seismic behavior. We can animate this here and see how it kind of bounces up and down in that direction. Right, again, keep in mind that this is a high deformation scale just so we can actually see the movement. But you see that, again, the way we would compare these results, seeing what the max stress is and seeing if that's going above yield based on any of the yield points that we've defined in the material property. You can take a look at our displacement as well. You see it's displacing very little here. So in this case, we can meet that standard, or we can take a look at that standard and see if this fits the criteria that's been defined. So we go from a linear static. You see that in a linear static, we define a gravity and multiply by a huge load, or we can input seismic information through that response spectrum, but we still don't have information of how those stresses are being developed from beginning to end. And that's essentially what a time history analysis will do, which will probably give you the most accurate or the most information because we are getting what those stresses are as a function of time. And so this allows us to input or do a virtual testing where the input may respect to time if we wanted to do some sort of shock loading or impact loading or impact testing without having to do the physical test. Often conducted to this information is usually provided through the mill standard 810F method 516.5. That's a lot of the examples that we have, especially in our training, refer to that specific standard. But you see that what we have, again, is our inputs are the material definition, the fixtures, but now the loading is a function of time. And we have the option to input some sort of damping ratio as well. And the output we get are, of course, stresses and displacements, but now at the different time steps, and we can actually see in a curve what the response is. So going back to our interface, we can take a look at a time history. Again, and the beauty of a linear dynamic problem within simulation is once you're familiar with one type, the workflow is essentially the same. The only thing that really changes is going to be the actual input, right? So everything, the setup's the same, but now when I go into the base excitation, you see that I'm still defining it, still want to impose some sort of acceleration load, but now my value is I wanted to experience 20 Gs again in that downward direction, but now I want to impose the shock loading. So this is something that we can't do within a linear elastic where again it assumes the loads are being applied slowly and gradually. Here with the time history analysis, we can define that the load is being applied at 11 milliseconds, and then it turns off for the rest of the analysis there. So we want to see what the stresses are when there's this impact or this shock loading for this type of scenario in the downward direction there. So when we accept that there, we then can define the actual damping ratio here. So we can say that it's going to have a 2% damping, at the running through this analysis here, and we can actually see those results taper off in our response graph. So when we take a look at our stress, again, typical stress result, right? We can see where the max stresses are, but note that we're now seeing where the max stresses are at a specific time. So you see I'm looking at the stresses at 11 milliseconds now, and I have the option here to change the time step. Maybe I want to see what it is at the beginning here at 0 seconds at the first time step, and we can increase what that value is and see how does my result change due to that different time step. And you see that it deformed actually a little bit differently here. We can animate this, which is pretty nice. So if you pay attention to the actual timestamp here, you can kind of catch like in the 11 millisecond range, how you see how it's actually bouncing off. You see that the damping ratio there is being accounted for. So again, now we get more information in terms of how the stress is being developed throughout the entire time span. Okay. We can take a look at the displacements again. Same concept. You see that we're looking at the displacement at different times. I can adjust that time on the fly, create multiple plots here and that specify that are linked to different time steps, or I can animate this as well and kind of see how the behavior is going to look like for that 1 second time frame that I've defined. Okay. And then the last thing that we can do with this as well now is, again, since it's a function of time, we can take a look at the actual response. And we're looking at what the displacement is as a function of time here. So you see kind of at the 11 millisecond mark, that's where it deformed the most. And then eventually it kind of idled off, again, due to the damping ratio that we've defined. So we met that criteria, or we specified that criteria based on the standard that we've applied here. And you see how the deformation essentially is lowering as the load is being applied, throughout the entire time frame. So this is what we can do with the time history analysis, right? It's going to give us more information because there's more inputs that we can actually define. Similarly to a time history, we can also do a harmonic study. So this represents us being able to represent like some sort of shaker table or some sort of vibrational test, where now our input is very similar, some acceleration, but now as a function of frequency. And the outputs are going to be essentially the same. Stresses and displacements, but now as a function of frequency, and being able to see the result response from there. So taking a look at that here, if I switch over to harmonic analysis, same setup, but now our input is going to be same 20 Gs in the downward direction, but now our variation is going to be as a function of frequency. And essentially what I define here is I want to make sure, or I want to see what the results are based on this 20 G acceleration throughout this frequency range from 0 to 2000. So it's pretty much constant throughout that entire frequency range. And when we view our results, it's going to be a very similar fashion where we can then see the different frequencies that are defined here and the overall how the model is going to deform. So again, it's amplified to the deformation scale, but we may be looking at this, is this concerning, is this deforming enough for us to have to change something about the model? We can take a look at our displacement plots, and you see that really what's deforming the most is the transformers there, and it's only displacing 0.0012 millimeters. But we can take a look at that again and define a response graph very similar to the displacement in the y direction, and we can see at what frequency does it see the most displacement, and you see it's kind of in the 800 hertz range that falls within that range that I've defined in my frequency analysis. All right, so far what we've seen is, to account for shock loading, some vibrational loading, or some sort of seismic, we have a lot of different tools that can, take us from a very simplistic linear static with a conservative assumption, or a more complex dynamic analysis that gives us more freedom, more opportunity to input these different scenarios, different load conditions, and therefore getting us more realistic results and more accurate results here. So that's essentially what I had here. Really, again, just to break it down, we started off with the linear elastic study that comes when SOLIDWORKS Premium Simulation Standard. We then define the seismic response spectrum analysis. That, is a little bit more realistic because we're inputting what those load conditions are, but it's not going to give us a lot of information like a time history and harmonic study from the other additional dynamic problems will give us, because our inputs are a function of time or frequency, where we can see those stresses at those different time steps. Okay, so that's all I really had for you here. I do have a couple questions here. Let me see if I can read them off here. Do I have the number mil-spec that referred to? Yeah, so I think you may have seen it in one of our slides. I know for the time history one, this is referencing the mil standard here, standard 810F 5165. Again, if you were to take a class with us, that's what it refers to a lot within the standard. So that's where this information pretty much came from. So there's a question about mesh. So didn't really cover much about the mesh here. We have the same options, or same options throughout the entire different study types. They don't really change from one study to the other. Really, what we have the option, what I ran in this test is just the automatic mesher. I define curvature-based mesh because there's a lot of curve-based features here. So what that's going to do is going to automate or automatically resize and refine the mesh in those small curvature areas. If this was a real case scenario, we would want to apply the stresses, or apply a mesh control, which is pretty much refining the mesh in localized areas in the critical areas of concern. So it may be all the components, it may be just the PCB board. We can choose the components here, refine, make this value smaller, and pretty much increase the accuracy of those components by refining the mesh a little bit further there. Okay, so that's all I really had for you there. I think there's maybe some additional questions that I'll answer after the fact here. But essentially what where I want to end this now is just want to thank you for joining me today for today's webinar Wednesday. Again, we do this every Wednesday at 11 o'clock, and we have some topics coming up in November, some pretty good ones here. One relating to SOLIDWORKS. The week after will be SOLIDWORKS Composer, some tips and tricks. 2017 just got released, so there's some new functionalities with our different softwares. So November 16th will be CANWorks, and then we'll end the month with some information on data migration for SOLIDWORKS PDM. So again, I just want to thank you. If you have any other additional questions, feel free to answer them within the chat, and I'll get to them here. If not, if you have any questions about packages and pricing and things like that, you can contact your local account representative or give us a call, and we can kind of link you to that person. If you have any technical support questions, any issues with your software, or any technical related questions, you can go ahead and give us a call through our tech support line as well. Again, just want to say thank you, and have a good day.